Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Part 3 of Chapter 7, Analysis of Covariance. So we'll scroll on down to Lecture Notes, Analysis of Covariance. And in the last video, we were looking at a data set of twins who were separated at birth, one twin raised by their natural parents and one twin raised by foster parents, and comparing whether the IQs, how does the IQ for the natural raised twin help predict the foster raised twin's IQ relative to their social status, either low, medium, or high. The low group is the baseline group. The high group is indicated by an indicator variable I1, and the medium group by I2. This was our full interaction model, where we've got slopes for each status group, as well as, those are intercepts for each status group, as well as slopes for each status group. And in the last video, we went through, I'm paging down, we looked at the full interaction model. That's the data, and we found when we fit the interaction model that the interaction term for whether there's differences in slope was not significant, which suggests that all three slopes are the same for the different status groups. So I'm going to scroll on down, and we will now simplify our model and look at a model that allows for different intercepts but one common slope. And so one example visually of that could be this, where we've got parallel lines, that's our equal slopes, but we have different vertical offsets, which would be different intercepts. So here our model, we have a main effect for the slope and the main effect for the status groups, which are the different intercepts. When we look at the Anova table for this, first we're comparing whether we've got, say, difference is, let's do this one, IQN. Is the slope different from 0? And this suggests very much so. Are there different intercepts? And here this is a 2 degree of freedom test. It's asking whether all three intercepts are equal, and we have a p-value of 0.2. So that's suggesting to me that we don't have enough evidence to say that there's differences in intercept between status groups. And that would be where we would perform the next model selection step. Let's go through and interpret this model, however, for pedagogical reasons. So if we look at the summary for this model in the coefficient tables, these are the coefficients in the model that we saw above. We have an intercept for the baseline group and the slope for the baseline group, and then we have offsets for differences in intercept from the high group relative to the baseline low group and the medium relative to the low group. We don't, as I said in the last video, we don't have a comparison between high and medium groups here. These tests indicate whether there's a difference between the high and the low group. But ultimately, we don't care about those hypothesis tests because we found above this test to be not significant already, whether all the intercepts were equal. All right. Just for pedagogy, let's write out what the fitted model equation is for our three status groups. We have our low group, medium group, and high group, and the predicted foster child's IQ is the intercept and the slope for the low group. So if can we get both on the same screen? Oops, sorry about that. Jumping around. All right. So here we have the intercept for the baseline group, 5.6, and the slope for the baseline group 0.96, excuse me. And then these are offsets for intercepts for the other groups. Let's see if I can get enough of this on the screen if I zoom out just a little bit. Nope. And just barely. Okay, so the medium group offset is negative 4.19. Foiled by my... Alright, so that's the intercept for the low group. This is the intercept for the medium group, the offset, and when you combine them, this then becomes the predicted intercept for the medium group. Same slope though, right? This is the equal slopes model. And then same thing for the high group. Here's the offset you combine. There's the intercept for the high group. Okay. So another model, so that ends the equal slope but different intercepts model. Here's another model. We could have equal slopes and equal intercepts. What would that even mean? That means if we have equal slopes and equal intercepts, we have one single regression line to describe all three groups. So here we are, intercept and slope. And we've effectively set the other regression equations or regression coefficients equal to 0, starting from the model previously. So if we fit this model, so that relating the Foster IQ to the natural IQ, we can test whether, oh sorry, using my keyboard poorly today. We can test whether that slope is different from 0, and in fact we have evidence that it is. And here is the intercept and the slope. And those are the numbers that I put in here. So that is the model for this. That's the fitted coefficients for this model. Okay. And finally, a model that doesn't apply for, so in the case of model selection for this data set, I think this is probably the best and simplest explanation for the data, that we have a common intercept and slope for all the social groups. And that slope is sort of close to 1.9. Another model, which is a special case here, is that the slope equals 0, but that we have different intercepts. And that is a model you've seen before, though not in this form. This is the Anova model, the analysis of variance, where we have the mean for, say, the baseline group, the low group, and then I1 and I2 help indicate the coefficients for the high and the medium groups. And so this is really just, we've got three means. We have beta naught, we have beta naught plus beta 1 for the high group, and we have beta naught plus beta 2 for the medium group. Those are our three means, just in analysis, just like in analysis of variance. And this is just another way to parameterize or write out in equation form that model. So that sort of looks like this. Okay, slopes are equal to 0, but different means. And so at the end of the day, we don't care about the IQN. We only care about the means, the differences in foster twins based on social status. And so if you fit this model, as I do here, just IQF relative to which status you are, we can do the 2-degree of freedom test of whether all the means for the foster kids are equal relative to the statuses. And here we've got a large p-value. So this suggests that the foster IQ doesn't depend on your social status. And the three means, the low group mean is basically 93. The high group adds 9 points to that, so it gets you up around 102, 103. And the medium group subtracts 4, gets you down around 89 IQ. So those three fitted equations are here for the low group, the high group, and the medium group. All right. So let me page down for a second. And I'm just going to skip this section. Go ahead and read it, but it's I think we've covered all the details here. All right. So choosing among models. So in terms of finding a parsimonious model, that means sort of a simple model, following what's called Occam's razor, the principle that you choose an explanation that is as simple as possible without losing the important complexity. I recommend using backward selection for model selection, though there's lots of types of model selection and there's criticisms of every type of model selection. So at the end of the day, it's hard to win against critics for model selection, but you need some principal way to start with your ignorance and then end data and learn and come up with an explanation of what patterns exist in the data. And the reason I recommend backward selection is you start with the most complicated model that is reasonable, and then you do a series of hypothesis tests to simplify the model, but not make it too simple. Okay, and actually that's sort of what we did in the previous section. I recommend that you go ahead and read through this section. It does follow some of my explanation for how we went through the previous models in that previous section. All right, the last section of the notes discusses how can we test simultaneously several parameters at the same time in a regression model. We've seen cases. Let me page up for a moment so we can get a sense of what I mean. I'll go to an earlier model. Here we have got the main effects model with a slope and intercepts, and we had this 2-degree of freedom test here of whether all the statuses were equal to each other. Now, what does it mean for all the statuses to be equal? That means in this regression model, okay, in this regression model, all the statuses are equal. That means all the intercepts are equal if beta 1 equals 0 and if beta 2 equals 0. In that case, both of these terms go away and you're left with a common intercept for all three groups and a common slope for all three groups. And so this is a 2-degree freedom test. We're testing whether beta 1 and beta 2 simultaneously are equal to 0. Okay, but there's lots of other interesting combinations. In fact, the model that we are looking at right now is the model after assuming that beta 4 and beta 5 both equal 0, meaning we don't have different slopes. So if I page up for a moment to the full model, the full interaction model, right? If beta 4 and beta 5 both equal 0, then all that in blue goes away and we only have one slope parameter for all three groups. And so you have to sort of think about, well, what other combinations could be interesting? Well, maybe I want to test whether the medium and the high group are both have the same regression line. How would you get both the medium and the high group to have the same regression line here? Well, the medium group and the high group would need to have the same intercept. Okay, and so if this is the offset from the low group for the high group and beta 2 is the offset for the medium group, then if they're going to have the same offset, then beta 1 and beta 2 must be equal. Similarly, if the medium and high groups are going to have the same slope, both beta 4 and beta 5 need to be equal. And so in that case, boy, that's sort of a complex hypothesis. How do you test whether both beta 1 and beta 2 are equal to each other and beta 4 and beta 5 are equal to each other? So that is the content of the next section. All right, simultaneous testing of regression parameters. So here are two examples. I think I build this to the one I just gave. All right, let me page up. Start simple. Stop jumping around. All right, so let's first test equal regression lines for the medium versus the low group. Okay, so low is the baseline group and medium. So, oh yeah, hypothesis 2. This is the one that compares medium and high. Great. So we've got medium versus low. So how do we test medium versus low? Well, what would that mean? So beta naught is the intercept for the low group. Beta 3 is the is the slope for the low group. I2 is the indicator for the medium group. So if low and medium are going to be equal to each other, then what does beta 2 need to be equal to? 0, right? Because that means this term doesn't change when the medium group is active. Similarly, here's I2 for the medium group. If beta 5 equaled 0, then when you're the medium group, then your slope would only be beta 3 plus beta 5. Beta 5 is 0, so you'd be beta 3. All right, so we want to test in this first hypothesis whether both beta 2 equals 0 and beta 5 equals 0. And then I guess we've already talked about this one, medium and high groups, right? Medium and high need to have the same intercept, so beta 1 and beta 2 have to equal each other, and same slopes. Beta 4 and beta 5 have to equal each other. All right. All right, so here's our answers for those two hypotheses. And one general strategy is to use something called the Wald test. The Wald test is a strategy for performing these types of hypotheses where you specify the hypothesis test in terms of a matrix R. Oh boy, this is awful notation. We've got R as a matrix of coefficients as well as this R vector of values that it equals. All right, so we have to talk a little bit about matrix multiplication in order to understand how this works. Beta is our beta vector. Okay, so we've got our beta vector, beta 0 down to beta 5, a list of numbers. And this matrix notation is going to leave us with two equations. Let me page up for a moment. It's going to leave us with an equation beta 2 equals 0 and beta 5 equals 0. Those are our two equations that we want to write using the matrix notation. So the way matrix notation works, and this is the worst way to teach this via a video waving a little cursor around. We want to, so we've got so we have a matrix on the left-hand side, and this first row of the matrix will end up being multiplied by this column of betas, and will end up equaling this first row of the vector on the right-hand side. And the way the matrix multiplication works is like this. And probably at this point that you want to Wikipedia this so you get it. So we have to take the first coefficient, 0, times the first value here, beta naught, and you multiply them together. Then you add that quantity to the next pair. So we're going to go from left to right on the left matrix and top to bottom on this vector. So we've got 0 times beta naught plus 0 times beta 1 plus 1 times beta 2 plus 0 times beta 3 plus 0 times beta 4 plus 0 times beta 5. All right, so every pair, one thing I do with my hands, which you can't see, is I'll use my left finger to point at the row vector on the left, and I'll take my right finger and I'll point to these values on the right. And every time I put both my fingers down, I multiply. So I hit my left finger on 0, my right finger on beta naught. When I do that, I multiply. Then I lift my fingers up, and then I put them on the next value. And when I lift them up, I add. So multiply 0 plus beta 0 times beta naught, lift the fingers up, plus the next one, 0 times beta 1. Lift them up, add, and so on. All right. And at the end of the day, what do I get? 0 times beta naught is 0. 0 times beta 1 is 0. 1 times beta 3, or sorry, beta 2. So really, all this simplifies to just 1 times beta 2, which is beta 2, equals 0. And if I page up for a moment, that was what I wanted as my first equation. Okay, my second equation is beta 5 equals 0. And so notice, all the first terms are all equal 0, and then I have this one indicator variable 1 times beta 5 to give me beta 5 equals 0. Possibly the worst explanation of matrix multiplication, but I doubt it. All right. So typically you'll fill this matrix on the left-hand side with sort of positive or negative 1s to indicate which betas are in your equation, and you'll often just have that equal to 0. All right. So let's look how to do that. Let's see, do I have that as the Wald test coming up? Okay. So here is in the AOD library, that's where we get the Wald.test function. And there's actually a couple ways to perform this Wald test. Do I do it both ways? Page down for a second. Okay. I'm going to show you the more complicated way because this is more general. Okay. So here I'm going to define that matrix. So I've got two vectors here. Okay. Oh, you know what? I need to tell you something else about this. The order of the coefficients may be different than the order that we had in our handwritten model. So let's see. That's where this is important. Okay. So let me scroll down just a little bit. Let's look at the coefficient order. So we have the intercept, that's beta naught. Then we have the slope parameter, that's beta 3. Okay, so it's in a different order than we had in our handwritten, typeset notes. Then we have the status high group, that's beta 1. Then beta 2, that's the intercept for the medium group. Then we have the slope for the high group, that's beta 4. And then the slope for the medium group, that's beta 5. Okay, so it's in a slightly different order. We have beta naught, 3, 1, 2, 4, 5. Okay, and all right. And in terms of the position, okay, I'm going to ignore that. So let's scroll on down to where I do this as a matrix. So we want beta, let me remind myself. Okay, we want beta 2 equals 0 and beta 5 equals 0. So page back down. So this first equation is going to indicate beta 2. So we have beta naught, 3, 1, 2. Okay, and then the second equation is beta 5 equal to 0. So this matrix, I'm going to take these two rows, and R-bind binds the two rows on top of each other. So we have the first row here, sort of, and then the second row here. And so there's our 1 for the first equation and the 1 for the second equation. That's the left-hand side R, that's the matrix R. Then we have the vector R on the right-hand side. This is just two numbers, 0 and 0. And then here's our Wald test. So we set B as our coefficients. That is, if I page up for a moment, that's this vector here. That's our beta vector. And then we need to tell it about the left matrix and the right vector. Page down. So we have the left matrix, MR, so that's this here. And then we have the right vector, which is specified in this case as H0. That's sort of the null hypothesis. And the last part is we need this this variance covariance matrix from the coefficients. So you just plug that in from the regression fit. And this is the linear model from the full model. All right. Boy, that seemed like a lot of work. I apologize. But that's how you do it. Finally, you get this Wald test. It's a 2-degree of freedom test. And we have an insignificant result here, suggesting that, in fact, beta 2 and beta 5 simultaneously are both equal to 0. Or at least we don't have evidence that they're different from 0. All right, so that is that first hypothesis test. If some of that was confusing, go ahead and read more of the text and see if that helps. Let's look at the second hypothesis test, where we want to test whether beta 1, so this is whether the medium group and the high group are different from each other. So beta 1 and beta 2 are equal, and another way to phrase that is that beta 1 minus beta 2 equals 0. That's the intercepts are equal, and then here is the slope equal to 0. Beta 4 and beta 5 equals 0, the difference. So in terms of beta 1 and beta 2, notice beta 1 basically has a positive 1 in front, and beta 2 has a minus 1 in front. So here's the order, right? Beta 0, beta 3, the slope parameter for the low group. Then we have beta 1 and beta 2. So those values, positive 1 and minus 1, are right from here. Then for the slope parameters, we have positive 1 and minus 1 in front of beta 4 and beta 5. That's those values there. If we turn that into a matrix, we get those two rows in a matrix. The right-hand side are both equal to 0. That's this value here, 0 and 0 in those hypothesis equations. And then I just plug them in. Here's the betas. We need this variance covariance matrix as sigma, and then we've got the matrix on the left-hand side and these two zeros on the right-hand side. And when we look at the result of the Wald test, in fact, the medium and high groups are not significantly different in terms of their regression lines. Okay, this strategy, using the Wald test for testing these multi-parameter hypotheses, is a really critical point. Basically, if you can, the main ideas in this chapter, I believe, are, if I just give sort of a quick summary right here in the middle, is understanding how to use indicator variables to parameterize a model with different intercepts and different slopes, and then being able to appropriately use something like the Wald test to perform hypothesis tests within that regression model framework. All right. And I'll let you go ahead and read this last section on the comments on comparing regression lines. Now, we've looked at two-way interactions. There are, in fact, you can go as many interactions as you have predictor variables. Okay, and I do give an example here at the end of a three-way interaction, and I'm not going to bother showing what this looks like, but it does give several different models and what those different interactions look like. And maybe you want to save looking at this too carefully until you need it in your own work. And that is the end of Chapter 7.